Basic Calculus 9, Graph Sketching Part 4, involving the graphs of derivatives. There we are, we've drawn f of x with the derivative of f of x and the derivative of f prime of x. So f of x, f prime of x, f prime prime of x. How do we know that's the case? Well, that's a cubic. Two stationary points, we can assume that's a cubic. Now from there, if we differentiate it, we end up with x squared, which is a parabola. And the blue graph, there's your parabola, f prime of x. And if we differentiate this one, we end up with x's, in other words, a linear function, a straight line graph. So there is the function, its derivative, and its second derivative. Let's have a look again in bits. At that point, we stopped it there because the derivative is 0. And there's a turning point there. Now, is there any reason because of that? Is there any reason for that? F prime has an x-intercept. F has a stationary point. Yes, because f prime is 0 there. And the stationary point occurs when the derivative is 0. The second derivative is 0 now. The second derivative is 0. Well, if second derivative is 0, it means the derivative has a stationary point. Because this is the red is derivative of blue. So when red is 0, blue has a stationary point. But we can go further than that, because when the second derivative is 0, what does it tell us about the original? Well, it tells us that it's neither concave up nor concave down, and there's a change in concavity between concave down and concave up. So it's a point of inflection. And once again, we have the derivative 0, which means we have a turning point on the original graph. The fact that the turning point is at this point as well is merely coincidental. The graph, the derivative, tells you nothing about the original vertically. This graph could have been drawn down here, up there. It'll still have the same derivative and second derivative. Because whether this graph is down or up depends on constants added at the end. And when you differentiate, those constants go. So let's just have a look at the two of them, the derivative and the function. Function and its derivative. Now, there are 2 points there. What do those have to do with f prime, the blue one? Pretty obvious, eh? X-intercepts. What do they have to do with f of x? Well, have a look. Stationary point, stationary point. The turning points. So there they are. So therefore, when it says, what does the graph of f prime tell us about the graph of f? Well, it tells us that the x-intercepts of the graph of the derivative are the x values of the turning points of the function. Why? Derivative equals 0 at turning point. Why have we divided into red and green sections? There we are. Above, below the axis. Now, above the axis, f prime above the axis means f prime is greater than 0, and below means f prime is less than 0. Well, have a look at the red and green sections there. They're drawn so that this one coincides exactly with that green section. F's red coincides with f prime's red, and f's green coincides with f prime's green. How do these sections, that green relate to that, where that red relates to this, where that green relates to this? Here we are. Where green is above, the green of f prime, the green of f is increasing, positive gradient, there, there. And where red is below, where the derivative is less than 0, the function's decreasing, the negative gradient. Now let's have a look at the second derivative and the function. What is this red? Well, first of all, why have I drawn red and green there? Quite simply, below, above the axis. Now have a look at this correspondingly drawn there. What do you know about that red compared to that green? What's f of x doing? Concave down, concave up. There we are. So therefore, we call that point the point of inflection, and it corresponds with when the second derivative is 0. Let's have a look at an example. The graph represents the derivative f prime of x of f of x. Don't see that as f of x, it's f prime of x. So it's not the original function. But this is a straight line graph, so the original function, you could say, well, what does x come from? It comes from an x squared. So the original must be a parabola. Values of x for which f of x is decreasing and increasing. Now, the value for which f prime is less than 0 and giving you less than minus 3, and f prime is greater than 0. That section there means that the derivative is positive, which means that the function is increasing. So x greater than negative 3. Coordinate, x coordinate of the stationary point, there are x equals minus 3. Notice x coordinate. This graph cannot tell you anything about the y values other than the behavior of the y values, increasing, decreasing, stationary points. It cannot tell you anything about the actual y values of f of x. That's why this is a misleader, because we can't use this fact that that is 2 there at all at this stage. So we have to say whether it's max or minimum. Well, because f prime is less than 0 before and greater than 0 after, must be a minimum, just looking at the shape. Another example, this time the derivative is a parabola, which means the original function must be a cubic. Once again, the graph represents the derivative. At this stage, that negative 2 tells you nothing about the original function. That's just a y value of negative 2 on the derivative. Well, that tells us nothing about the original. This turning point doesn't tell us anything really about the original either. What tells us is these 2 points here and whether this graph is above or below the axis. Right, so values for which f of x is decreasing. Well, that means f prime must be less than 0. There we are. There's f prime less than 0, and that means f of x is decreasing. The x values between minus 5 and 1. Increasing, well, they're the sections where f prime is above the x-axis, greater than 0, and that is 2 sections to the left there or to the right there. The coordinates of the stationary points, well, there the stationary points are right there at f of x equals 0. So there we are. Determine whether the stationary points are minimum or maximum. Well, I'm going to look before the stationary point. Before negative 5, there's an increase. Between the 2, there's a decrease. And after 1, there's an increase. Well, increasing means it's a positive gradient, negative gradient, positive gradient. So we have a maximum at negative 5, a minimum at 1. Draw a sketch graph that meets the criteria found. Well, let's set it up there. There's the axes with the graph. There's a vertical line at the x-intercept, and at the x-intercept, meaning this is the x value of the stationary point of the original function. So as long as the stationary point sits on that line and on that line, and as long as the maximum sits here and the minimum sits here, we can draw whatever graph we like. There we are, maximum, minimum on those lines. We could draw that instead, that's fine, that's fine, that's fine. Any one of those is acceptable. Once again, the graph of the derivative tells you nothing about where the original is placed. So points worth noting. Stationary points occur when the derivative is 0. When the graph of the derivative has x-intercepts, then the original function has stationary points. The function is increasing when the derivative is positive, or in other words, when the graph of the derivative is above the x-axis. Here's the graph of the derivative, f prime, there's the original. It's above the x-axis there and there, so it's increasing there and there. And the function is decreasing when the derivative is negative. Here the graph is negative, the derivative is negative below the x-axis. There's the original graph decreasing. So just to summarize here, positive gradient, negative gradient, positive gradient. There's the function. So we know that's a maximum because it's increasing then decreasing. We know that's a minimum because it's decreasing then increasing. Now notice my wording is slightly different from the diagram here because I say maximum when the derivative is positive then negative. Gradient positive then negative, but remember the derivative gives you the gradient. And minimum when the derivative is negative then positive. Now when the derivative is negative for this red section, it means it's below the axis, and when it's green, positive gradient, that means the derivative graph must be above the axis. So there's the graph of the derivative. Summary. Stationary points occur when the derivative is 0. The graph of the derivative cuts the x-axis. Function is increasing when the derivative is positive. In other words, the graph of the derivative above the x-axis. Function is decreasing when the derivative is negative. In other words, the graph of the derivative below the x-axis. Maximum when the derivative is negative, then positive. Positive, then negative. Going upwards for positive and downwards for negative. Minimum when the derivative is negative, negative gradient, then positive gradient. There's our original diagram there that we started with. And here's one to relate to it, where it's now got a degree 4 expression with 3. It's a minimum there, a local maximum there, and a local minimum there. Now we're going to have points along dotted lines. So if we start, there's a dotted line there. I've drawn it there because the derivative, the red graph, has an x-intercept. What's the relationship between those dots? What do they have to do with the functions? Well, x-intercept on the derivative, which means derivative is 0, on the function, stationary point. Moving on to the next section. Now the green has appeared. The second derivative is 0. Well, the second derivative is derivative of the derivative. So when the second derivative is 0, it means the derivative has a stationary point. But also when the second derivative is 0, it means the original function has a point of inflection. Concave up, concave down. Back to the red, the derivative, x-intercept, and stationary point for the function. Back to sec derivative intersecting, sec derivative 0, turning point for the derivative, point of inflection for the original. And finally, once again, derivative 0, stationary point on f of x. Some exercises for you to try. Pause, do them first, then go through the answers. This is the derivative. For what values of x is g, not g prime, g increasing? Well, g is increasing when this is positive above the x-axis, greater than -1. Decreasing when g is below the x-axis, to the left there, less than -1. Give the x value of the turning point of g of x. Well, there's the x-intercept where the derivative is 0, and that gives you the indication of the turning point. So it's at x equals -1. With reasons whether it's maximum or minimum. Well, before -1, it's decreasing. After -1, it's increasing. There we are. So that's the shape. And that's a minimum. Now we have to find A, B, and C, right, where g of 0 is -2. Now we are going to use the y value there. You'll see why in a moment. But g of 0 equals -2 is the easiest for a start, because if I substitute that, it gives me that c is -2. We've been given the y-intercept of the original graph. Now, we know nothing else about the original graph. We only have facts about the derivative. So what we're going to do is we're going to differentiate that to get the derivative. There it is. 2a plus b, and c is gone. There it is. Now, we can find values here. We know that f of 0 is 1. So when x is 0, y is 1. So we can substitute into that. And that's quite useful, because that gives you our value of b. Once we have the value of b, we can now put b in there, and we can substitute the other point, -1, 0, into the equation. And that gives us the value of a. We still need to sketch this graph. Which means there's the equation. We need the y value of the turning point. We know the x value, -1. We need to know the x-intercepts. And we know the y-intercept we've been given it. So, there we are. I've substituted -1, the x value of the turning point of f, and we get -2.5. So there's the turning point, the stationary point of g of x. Put this equal to 0 and solve for x, and there are the x-intercepts. And that gives us our graph of g of x. Second question. Now we have the parabola, which means this, and this is a derivative, means that it's the derivative of a cubic. What values of x is f increasing, decreasing? Well, we're going to say, where is f prime positive, f prime positive, f prime negative? There we are. Oh, this should be f, not g, sorry, but it's negative from 1 to 5. So therefore, that's where the function is decreasing. And positive from but before 1 or greater than 5, so that's where the function is increasing. There's the actual values of the turning point, the x-coordinates. Note it can't tell you anything about the y-coordinates. So there is the function there. There's the x-intercepts there and there for the derivative. So therefore that and that are the x values of the turning points. Now, positive, negative, positive, so therefore we now have that shape. Now we have to find A, B, and C. Well, I'm going to find f prime of x. There it is there. And we know enough about this graph to pick up everything. F of 0 is 5, so therefore C is 5. F of 1 is 0, so it gives me one equation. F prime 1 is 0, F prime 5 is 0, there's the other. So all I'm doing is I'm substituting 5, 0 into there and 1, 0 into there. And I'm going to solve simultaneously. Subtract the equations to get rid of the b. I've done 2 minus 1, so we have a positive here. So a is 2. Substitute back, and we get b is 5.5. So we have a, b, and c.